Okay, so before we get started, note that we have 2 quizzes this week. And the reason we have 2 quizzes this week, even though we're still doing 1 chapter, is because the second quiz, you need to see it before the midterm. And the midterm is next Tuesday. And the midterm is during class. And it covers through chapter 4, the chapter we're finishing this week. And remember what the midterm looks like. It looks like the in-class quizzes, which means it's, made up of various problems, that require some sort of thought or addition or multiplication maybe, or looking at a schematic like you'll see on the quizzes tonight and on Thursday. Okay, and so without any further ado, let's move on here. Any questions about that? Is my audio actually working? Is it working like it's supposed to?
Yeah,
Can you hear me out there? Anyone there?
Yes. Hi, Professor. I have a question about the Lab 5. So it's due next Thursday. So this week we don't have any lab work.
That's right. You're free of lab, right? You just want to prepare for the midterm. No lab. Okay, so here's where we left off. This picture here is a picture that illustrates our 5 pipe stages, and shows the pipeline registers that are between the stages. And so you can see exactly what has to happen in one clock period in this form of the diagram. And this diagram tries to help you a little bit by showing you, for a particular kind of instruction, what things are being used. For example, in this load word instruction, it shows that the data cache is being used in the second half of the cycle, because that's when we're reading the data cache. Recall that we write in the first half and read in the second half, just like in the register file. In the register file here, we're reading the register file during the second half of the cycle. And here at the end of the instruction, we write the register file in the first half of the cycle. And that's important. We'll see when we look at the next couple of pictures with the, that has the arrows that show what we're going to try to do here. So there's actually two flaws in this diagram. There's basically just a copy paste error. This box should go here, and this box should go here. You see that this is an add instruction, so it shouldn't, be using the data cache. And this is the load word instruction, and it should be using the data cache. So there's just they just screwed up where these 2 boxes go. And then let's see, there was one other mistake in the diagram. Oh yeah, they left off a line here. Left off these lines, but that's pretty minor. But so it kind of illustrates very at a nice abstract level what has to happen in the pipeline for each of the pipeline stages, just showing the instruction cache, the register file, the ALU, the data cache, and then finally the register file again when we write it. Okay, so we're going to try to execute this sequence of instructions here. And we're going to immediately see that we're going to have some conflicts for resources, and that's what we're going to do now. Is we have to figure out, using everything that we've learned so far, how in fact we solve these problems. We know we have to do bypassing. The question is how does that happen? How do we get that to work? Come on. Come on. There we go. Thank you. So here's that same sequence of instructions shown with all 5 of the instructions shown at what point in the pipeline they are. You see that the first one, when it gets to the write back stage, meaning when it's basically done, the second one is one tick behind it, and so on, going back to the one that's just entering the pipeline now, this add. So again, we have 5 pipe stages. So there's one instruction who's finishing, and 2, 1, 2, 3, 4, 5 instructions later is one that's just starting. And so again, this just shows the pieces of the puzzle. This is, these pieces right here are the very first ones we saw in the very first, time we said, okay, what pieces do we need to actually execute these instructions? The pieces are the same. Now we just have these registers between them, so that we can, which allows us to pipeline it, which allows us to operate on all 5 of these instructions at the same time. So here he just takes the same diagram and sticks in the control logic at the appropriate pipeline place. Here's some here that's doing the ALU, and the important point here is that the logic that's controlling the ALU, that's telling the adder to add or the subtractor to subtract, whatever it's telling it to do, that has to be aligned with the data, so that the data for an add instruction, when it's coming out of the register file and registered here, we have to have the bits of the control also registered and available during that same clock cycle. So these things have to stay in step with each other. So you have to have the data going into the ALU, and the bits which tell the ALU what to do on those particular 2 data items. They have to be there at the same time. So they have to be pipelined along and kept in step. And here's just a picture showing, doing that. It says, okay, we'll take the instruction, all the instruction bits that are control bits, and we'll decode them into these signals. And remember, one of our favorite ones was the branch signal. And then we just, we'll pipeline it along. Every cycle it moves, right, from one stage to the next. We'll just pipeline it along until we need it. So here's the stuff that we need in the MIM cycle. So it gets pipelined along and then gets used here in the MIM cycle. The execution cycle bits get pipelined along once and get used here. And then the write back bits get pipelined along 2 stages and don't finally get used until here. So you have to keep pipelining along the bits that you need for that stage. So whatever you need for that stage. So for example, here we need the write register file. That's the control signal we need during the write back stage. So we decoded it back here somewhere, and we pipelined it along until we got to here. And that will be true for all the control signals. You just keep them marching along with the instruction, with the data of the instruction, until you get to the end. And so here he puts it in a little more detail. The detail isn't that important. The concept again is just, you decode it and then stage it along until you need it. Pretty straightforward concept. You do that for all of the control bits. You put them in, hold them in the register and let them move from register to register, just like the data does. That's all you need to understand. You just need to understand that the control and the data needs to stay together. All right, now we must open our minds very, very wide. So here's our favorite sequence of instructions. And when I say favorite, I mean that here we compute this subtraction into register 2, and then we immediately use it in the next instruction. We do an AND function with it. And then in the very next instruction, we do an OR with it. Okay, so this instruction, this sequence of instructions is going to illustrate a lot of things for us. So we'll want to pay close attention. One is that we will find out that this is the important window that we have to look at for bypassing. Because we saw before, and we'll see it again in just a moment, that once we get past this point here, that we can get this 2, and note that so this 2 has to go here, and it has to go here, and it has to go here and here. But we'll see in a diagram in just a second that here we're going to be able to just read it from the register file. But these 2 here we'll have to bypass. So again, that this is the window for bypassing. It starts with seeing that we have 2 here as the destination, and then we have to look at the next 2 instructions and see if that 2 gets used anywhere in those next 2 instructions. So that's the rule. Look at a destination. Destination is here on the left. And we'll note one subtlety in just a second, but in general, the destination is here. And so you look at a destination and then you look at the next 2 instructions down and you see if you find that number. And if you do, you know that there's a bypass required. And if you get down to here and you see it again, you know you're not going to need to do a bypass because it'll be read out of the register file. And here as well, this will be read out of the register file. Note carefully for store word, and this is the only instruction like this, because it's the only instruction that moves in this direction, that this is not a destination. This is a source, right? So if we had other instructions after the store word here, those don't follow let's look at this and see if the 15 appears in those next 2 instructions, because this isn't a destination, right? The store word has no destination register. So when you see a store word, you don't have to worry about looking past it to see if you need to bypass from here, because you're never bypassing from here. This is not a destination. It's a source. So just keep that in mind. That's the only instruction like that. So when you see a store, be careful. Okay, so here he poses the question that we need to answer. He says, we can resolve hazards with forwarding or bypassing, whichever word you like. how do we detect when to forward? So this is the key magic trick that we want to get into our head here is how do we do this? And this is the essence of keeping our pipeline going. The concept up to here of doing your laundry, in pipeline fashion is very straightforward and intuitive, I think. This portion here where we try to figure out how we're going to do this is not immediately intuitive. You have to think about it for just a bit. So you're going to want to think carefully now. So here's our picture with our sequence of instructions, and there's that 2 and the 2 and the 2 and then the 2 2s. And so the red line there, the red equals bypass or forward. The blue is saying, okay, here's all the places where we need that destination. We know that this 2 here is the destination and that it's going to end up in the register file, but it doesn't end up in the register file until here, until this point in time. That's when it gets written. But we want to use it here because we see that we want to use it there. So that's going to cause that first red bypass there. And then we also want to use it here. That's right there, that guy. So we need to bypass here because it hasn't been written into the register file until midway through this cycle. So we have to still bypass it from here. So we have two bypasses, and note that that follows our rule of finding the 2 here, and we got to look at the next 2 instructions. And that these 2 2s and this 2 here, those can all get read out of the register file. So that'll get read from the register file, and those guys will get read from the register file. Once it's in the register file, no bypassing is necessary. So once it gets past the write back stage. Once you can draw a line from the end of this blue to the beginning of this blue, that if you can draw that line, then no bypassing is required. And notice you can't do that here, right? From this blue to this blue is going backwards in time. Can't do that. So that's why we have to do this bypass here instead. All right. So somewhere in the next couple of slides, we'll see in a second, there's just a really ugly looking equation that says, okay, well, here's what you have to do this. So we're going to skip very quickly over that ugly equation. And we're instead just going to look at a picture that will allow us with, that being worth thousands of words will make it a lot easier. There's the ugly equation. Instead, we want to look here. Here's our picture of what we want to have happen. So here, so these guys here, these are new to our diagram. We've never seen them before. These are our bypass muxes. This is what allows us to get something from somewhere other than the register file. Note that the register file is one input to the mux. So when you're not bypassing, you're always just going to get the value from the register file, and that's going to be the path that you take. So that's the simple case. No bypassing. You just read from the register file, you go right through the mux, right to the adder, just like we've been saying for the last, week and a half. The normal case. Now, it turns out the normal case, of course, or the simple case is not the actual normal case in the real world. In the real world, we're almost going to be always coming through the bypass muxes rather than from the register file. So let's see that happen. So here's what happens, right? If we have an instruction, an add, or that subtract that we had, let's see, the sequence was subtract and the subtract source, was putting it in register 2 was the destination. And then we wanted to use, in the and, we wanted to use register 2. Okay, so let's see first the data path for that happening. And it's this line right here. So we take this thing, and normally if we're doing an add or whatever, it just goes around the memory. So just to go to the next stage, but we're going to grab that same signal and we're going to bring it here and be able to put it in to these muxes. You can go into either one of them. That allows it. So that allows that either one of these was an R2, either of the sources for the second instruction. We can put it into either the top or the bottom. And remember, by convention, that this is the top and this is the bottom, top and bottom of the ALU. So if we have and into R4 of R2, R3, then this is where the R2 is going. And this is where the R3 is going. So by convention, right, we just say this is the top column and this is the bottom column, meaning top of the ALU and going into the bottom of the ALU, going into the top of the ALU, going into the bottom of the ALU. All right, so that's the infrastructure. Now the question is okay, so how do we make that happen? How do we get this mux here to take this guy here as its input? How do we make this path happen? Path that I've drawn here. So the way we're going to make that happen is that it's kind of clear from the sequence. We have the subtract into R2, and then again we have the and that wants to use R2, so that we have to bypass there. And so the way we're going to do that is, well, we're going to note that okay, it's the 2 that's common here. That's the thing we have to note. And recall now that this destination field R2, remember, we have to carry it along with the subtract, because ultimately we have to write the result of the subtract into the register file at R2. So when we bring this data back, remember that we have to have the value 2 pointing to the register write port so that we write it into the right place. And remember, to make that happen, what we did is we took the R2, so we get it right here. So as the subtract is going down the pipeline, we read it out, we get a 2 here, and then the 2 moves to here, and then the 2 moves to here, and we'll take that same value here and have it be here. We'll see that in the next diagram, because that's the value we need to write it into the right place in the register file. But note that when this, and this is a 5-bit bus here, it's 5 bits, because it has to point to the place in the register file, that will be 2, that will have the value 2 on it when the original subtract is in this stage of the pipeline. So right after the subtract has done its job and the subtraction is complete, the result of the subtraction will be here, result of subtract. And the value 2, which is where it's going to get written into the register file, will be sitting right here on this 5-bit bus. And at the same time, the instruction after the subtract, which is the AND, it will be sitting here, wanting to AND R2 and whatever the other register was. And so these two values here, RS and RT, are the whatever this R here was, RX. RS will be 2. RS equals 2, and RX equals whatever that register value was. It was not nothing, it was something other than 2. And so what we have, you see, what we take the 2 and we feed it into this thing here called the forwarding unit. So this is a 5-bit bus also. So we feed 2 into our forwarding unit. Excuse me, we feed the value 2 on this 5-bit bus. And we feed the value 2 that's on this 5-bit bus, both into this forwarding unit. And what we're going to do is we're just going to do a compare. So we're going to go, does 2 equal 2? So we're just going to ask that question. So we're saying, does this 5-bit value match this 5-bit value? And if it does, that's what's going to cause us to flip this mux to take in this value. So that's the essence of it, is that we're keeping the place that we're going to write it to, the destination register. We're pipelining it along because we ultimately need it to tell us where to write into the register file. And not only does it tell us where to write into the register file, it tells us where we're writing, so that if something other instruction comes along and wants that value, we know that we know where it is. We know what it is and we know where it is. And so again, we just bring that value into our forwarding unit and we compare it against the current two values that we need. And if it matches either one of them or both of them, we're going to turn on this input to the mux and put it through. Okay. So while you think about that for just a second, let's just show the other case. So if we just go back for 1 second, where's our instruction sequence? So the next instruction was an OR, and it has the value 2 in the, so this is our RS field and RT field. And this goes into the top of the ALU and this goes into the bottom of the ALU. Just remember that convention. And so here we have this value 2, which is now in the second column. And it's in the second instruction, right? It's not this one, it's the next one. And so what does that mean for our picture? Well, it means that when that instruction shows up, the OR, so we have a subtract and then OR. When the OR shows up, the subtract has moved 2 ticks farther. Here it had moved 1 tick. Now it's going to have moved 2 ticks by the time the OR gets here. So we'll have the OR here, the AND here, and the subtract is here. By here, I mean like this. And so now what we're going to see is that our 2, the destination 2, is going to be here. So we have a 5-bit field that equals 2. And here we have RS and RT. In this case, RS is equal to whatever it was, and RT is equal to 2. So in this case, we're going to have, again, we're going to say, does 2 equal 2 for the bottom port? And it will say yes. And so this signal here will come up here and cause this guy now, because the subtract data is now sitting here. So now we're going to take him and feed him through, and he'll, whoops, we'll take him, oops, yeah, and feed him through the middle input of the mux. So the bottom input of this mux is from here. The middle input of the mux is from here. And the top input to the mux is from the register file. And note very carefully, we're about to look at another schematic, which when he drew it, he didn't follow this exact convention. So you have to note very carefully that he confuses, he changes where these arrows come from. And so you have to note that carefully when you answer the questions about where stuff has to go. Just note that don't assume that he follows this nice, simple convention here of where the arrows go into the muxes. Sadly, he did not for some reason. Okay, so again, we get the 2 equals 2. It turns on this mux. We bring this around, and now it goes through. And now the OR has its correct value. And then again, in the next cycle, the subtract is completely out of the pipeline now. And so anything that happens beyond here that wants that 2 will in fact, read it from the register file straight through the mux. No bypassing. So this thing will keep asking, the question, does the register equal 2? But the 2's gone. So the destination 2 value will have gone. So there won't be any more matches. So we can see that the next instruction that showed up after the OR was a something that wanted R2 in both, right? It had R2 in both top and bottom. But what happens here is that, we, in the one case, we had a 2 here, that's gone. And then we had the 2 here equal to 2, and that's gone because that was when we had the 2 here when the subtract was here. We had the 2 here when the subtract was here. And now the subtract is gone, right? It's moved off. Subtract is no longer anywhere in the pipeline. And the 2's have all disappeared from this bus. There's no more 2's here. So when that next instruction, whatever it was, should have paid attention. So when the add instruction gets there, so when we have the add here, the subtract is no longer anywhere in the pipeline. The 2's are all gone. So the Rx, the destination, whatever it was, R2 and R2 will both come from here, both come directly out of the register file. The normal case, if you will, even though the normal case hardly ever happens. Or at least it will hardly ever happen if you use the value right after you created it. Okay, so is that reasonably clear what you have to compare to do bypassing? We can now look at this ugly equation and see, and note that all this ugliness here just says the same thing we just said, right? It compares the D field, which is that thing we saved, and that's what's not clear. That's only made clear from these equations by the fact that it's saying, okay, take the EX mem one. So that's the one that's been, one cycle after it did the actual subtraction. And then compare that with the incoming, and that incoming means the IDEX, that's where it is in the pipeline. And compare it against both RS and RT. So it's comparing RD against RS and RD against RT, right? It's doing that comparison. And then one cycle later, so that's when the subtract is here. And then one cycle later, when the subtract is here, again, it does the same thing, but it grabs the destination bus one cycle later, now in the MW, mem write back pipeline stage, but again, compares it against the same RS and RT. The RS and the RT, you always use this from this stage. This is the stage that the add is happening in, that the incoming add that wants this value, it's always in this stage. And this is the guy that's moving along. And then again, you're always comparing against RS and RT. That's the two possible inputs into the ALU. So again, here he says you pass the register number along the pipeline. That's our RD value getting passed along. And the ALU operand registers are again the IDEX ones, RS and RT. So that's what he's using here. Again, and then always comparing against RD from the proper stage. So make sure you understand this notion. The good news is it doesn't get any harder than this. The next thing that we solve, we'll solve essentially the same way. But first we have to add some details to this. So what are the details that we need? So the first detail that we'll add is that we'll only do this if we actually have the value that we're staging along, that value 2 it was, remember the value 2, register 2. If the value that we're staging along is going to ultimately be used to write the register file. If that value that's on that bus is not actually a so-called valid destination, so it must be a valid destination. If it's not a valid destination, in other words, if it's not a add or a subtract or something that has a valid destination, then you don't want to bypass from it, because that means that the value that's sitting on that bus isn't something that you've computed and need to bypass. And so we'll just get asked ourselves here, what are the cases for that? And the cases, of course, are if it's a store, like we said, store has no valid destination, and neither does a branch, right? A branch doesn't write the register file. The things that do write the register file, so these don't, so don't write register file. And of course, the ones that do are, add and subtract and so on, and load. So we basically are again dividing up into our 3 classes of instructions, but here we split the load store. The load has a valid destination, the store does not. Branch does not. Add, subtract, all of the normal operation instructions have a valid destination. So that's this. So we'll add that to the equation. And then you never want to bypass if the destination, if RD is 0. If RD is 0, clearly you don't want to bypass from it because we're saying that the register 0 is always 0. So independent of what you try to write into it, it's going to be 0. So you don't want to bypass some number that isn't 0 into the ALU. You want to always get that 0 from the register file, because the thing that's coming on the data bus is probably almost guaranteed not to be 0. It'll just be some piece of garbage. And so here's our new equation with the extra stuff in it. says that here's our, it is a right. So it has to be a right. That means that it's a valid destination. We are going to write the register file. So reg write is equal to is 1, right? Reg write is true. And then here's the comparison, right? Here's where we're comparing RD against RS. And the only difference between these two equations is that here we're comparing RD against RT, and here we're comparing RD against RS. So conceptually, these two equations are identical. And then here we're checking that it's not equal to 0, right? Not register 0. So we just added, you know, to the original equation that we had. We just added these two qualifiers. So we'll call these terms qualifiers. Now I use that term, so you want to just be familiar with that term. They're qualifying and qualifying here, just basically it means, just as it says, they're anding, logical anding, right? So the comparison has to be true, and you have to be writing a register file because it has to be a valid destination, and the destination is not register 0. And then the rest of these equations are all conceptually identical. It's just that they're the other 3 possible MUX inputs, right? This is again the RT input, and then this is just RS and RT for the next cycle, right? This is coming from the write back stage. So this is called the execution hazard. This is called the memory hazard. And you know, they're just one cycle placed. So again, remember our rule is that, you know, we look down 2 instructions. And so these are the 2 instructions we're looking down from. Once we find a destination, we look at the next 2 instructions. And that's here and here. All right, so any questions on any of that so far? We're going to add another subtlety here. No questions. So here is a subtlety. It says, consider this sequence. And normally you would say, okay, well, if we follow the rule I gave you, there's always exceptions to every rule. If we follow the rule, we would bypass from here to here, from here to here, from here to here, because this is a new destination and we get a new window. And so all those bypasses would occur. But you can see immediately there's a problem with this picture. It shows, you know, a bypass from here to here and a bypass from here to here. And so clearly we don't want those both to happen because this value and this value aren't the same. So so we have to choose which one we want. And of course we want the most recent one. So we don't want this to happen. So a bypass that we normally would have occurred, we're saying, oh, we have to not let that occur. So basically we have to give priority to the most recently computed value. And that's this value here. right? That was computed after this one. And so this is the value that we want to go to here. And again, we don't want this value to go there. Okay, so how do we make that happen? So again, so we'll use this term. You know, we said that we have to give priority to the come on, we have to give priority to the most recent one. And so we'll use this concept of a priority encoder. And that sounds very fancy, but in this case, it's a very simple concept, is that we want this to prevent this, right? We want this guy here to prevent this guy here. And so what we do is that, therefore, is that the equation that we had for that guy there, so his equation, whatever it was, we'll say, and not this guy here. And so this we called the MIM bypass, and this we called the WB. So this we called the MIM bypass, and this we called the WB bypass, or it could be the X MIM and the MIM WB if you want to use both terms. So one of those, the first one is the X MIM bypass, and the second one is the MIM WB bypass in his nomenclature. And so we'll just take the equation for the X MIM and say, and not equation for the MIM WB. So we only forward if the execution hazard condition isn't true. Okay, so let's look at his equation. So here's where it starts to get uglier, but it's okay. All we did was we basically, you know, just took the other equation that we had from the previous page. That's that whole thing. And we just said, do this only if this isn't true. Right? So we're just giving a priority to them. We're saying, okay, if both these are true, only do the one that's from the most recent instruction. So we use that to knock down the other one. Right? So we want to this is the far one, right? The MIMW one here. The far instruction. So it's you know, you're bypassing from 2 stages away. So don't do that if it says that you want to bypass from 1 stage away. Okay, so that's subtlety, but it's very simple. Again, you don't have to worry about this. This is just the whole equation that we already learned for bypassing, you know, from nearby. So we're just taking and saying taking and using that again to knock down this one where it's trying to bypass from far away. So bypass from far away only if you don't want to bypass from near, where near and far just means 1 and 2, one cycle, one instruction away or 2 instructions away. All right. So that's the extent of our big ugly equation. And so here is where, again, if you look at this picture, remember where we drew it up here. Let's see. Oh, this one's right. It's the next one that's wrong. See, this one is still consistent. He still has this line going to here and to here. And he has this line going to here and to here. So this is still consistent, but the next one that we see will be inconsistent. So again, we'll just pay very close attention to how these muxes are hooked up to these 2 buses coming from down the pipeline. Okay, so here all he's done to this picture is added these extra signals, right? So we've got our RS and our RT going into our forwarding unit. We've got the signals that are the destination field that are piping along going in there. And now note we've got these signals coming down and going in there. And these are the what we call valid destination or reg write. So these are the reg write signals. And note these are just 1-bit signals. These are just single bit control signals. Can't tell, are they blue or black? It should be, I think they're blue. So the blue signals, again, are control signals, and they're generally, 1 or 2 bits, something like that. But in this case, they're 1, and that's just the thing that we're using as a qualification. So don't do the comparison. Don't flip this mux. If the value here, if this 5-bit value and this 5-bit value, if they aren't actually destination values that are going to cause, that are going to be used for a register write here into the register file. So if the instruction sitting here is a store or a branch, those signals will be low, they'll be deasserted, and therefore they'll prevent the forwarding unit from doing anything. And then all the other stuff about priority, the other 2 things, priority and not reg 0, register equals 0, that's all inside here. That doesn't require any other signals going in here, because 0 is 0. You just know to not do it if it's 0. You do that comparison inside here. And the priority, that's part of, you're just using the signals that you're computing inside there to just, you're reusing the signal that you already computed to prioritize which bypass gets turned on. So you can think about that. You don't need any other signals going in there to do these extra 2 qualifications. The only signals you need going in are the RS and RT, the 2 destination values, and the qualification signals. Those are the signals that you need going into that little box. And so you should understand what those signals are and what they do and how they do it. Hopefully I've explained that clearly enough here. All right. So remember we had, 2 kinds of hazards like this. We had the bypass hazard, which we just dealt with. And then remember, we also had the other one, the slightly more onerous one that we had to ask the compiler to help us with, the load to use hazard. And remember, the load to use hazard is caused by this problem here, is that when we do a load, so here's the load instruction, that unlike an add instruction where we have the result here, for a load instruction, we don't get the result until here, because we're using the adder to compute the address, and then we have another whole cycle where we access the cache or the data memory, call it data memory for now. And then we get the result here at this point in time. And we can't make this wire here happen. So he has a nice red circle around that wire because you can't do that. Because again, once we get to this point in time has passed. And so we can't get from this point in time to this point in time. It's not possible. We can only go down. So we can take that value and put it here, but this instruction here is going to have to just, get moved because otherwise he misses the value he needs. So we can get the 2 to here, but somehow we've got to get the 2 to here. And so the author says we need to stall for 1 cycle or insert bubble in pipe. And so that's what we'll see on the next slide here. Go to the picture and we'll come back to the ugly equations. So the and becomes a no-op. So that's our bubble. So bubble or stall, whichever you like. It's nice to think of it as a bubble appearing in the pipeline. It's like a bubble in a real pipe where water is flowing or something. There's a big space where nothing is happening. That's an air bubble in your pipe. So the and becomes a no-op here and has to move down to here. And once we move the and down to here, once we move it down a cycle, then 1 cycle has gone by, another clock tick has gone by. So now we can get the value from here and bypass it into here, and everything is happy. So here's the simple picture of what has to happen. And now the question is okay, how do we make that happen? And the good news is that basically the mechanism is exactly the same as it is for bypass. We just have to do it at a different place. We have to do it at a different point in time. And the question is, okay, well, at what point in time do you have to do? Well, now we can go back and look and see. We just need to find the schematic. So here's the schematic. And so here is our forwarding unit that we just learned about how it works. So it's still there, just doing the same old thing as it was. And now we have this load to use hazard detection unit here, as shown. And basically what goes on inside it is exactly the same. So here's RS and RT. So again, we're just taking RS and RT. We feed them both in. They're coming right out of the instruction here. And then we bring back RD. So we'll just show it from here. He picks it off from here because he happens to know that it's there because this only happens on a load. So he doesn't have to wait for the mux, but conceptually, we already know that we have that mux there to pick the right RD. So conceptually, we can just show it from here, take away a little bit of confusion. But this is fine too, and it's completely accurate because again, we know that the only time we're going to use this is right after we did a load. And we know that the load is in the RT slot, that the destination is in the RT slot. And so we can he just grabs it from there. That's fine. So we bring that into the box. And now we have the same things into the box that we had before. We have RD, and we have RS and RT, and we're going to do the exact same thing with them. We're just going to compare them. We're going to compare RD against RS and RD against RT. And the good news here, we only have to do it once. So all we're looking at is, are we the instruction right after the load? So there's no 2 instruction window or anything like that. We just look at the instruction immediately after the load, and we see, are we using the load? And if so, we have to delay that instruction by 1 cycle. Okay, so we know how to do the comparison. We're just comparing RS and RT against RD. If either one of them, in this case, it's very simple. If either one of them are true, if either of the comparisons are true, then we have to put in this bubble. So that's really, really simple. The hard part of this one is not that comparison. It's actually what we have to do after we detect that they're equal. And there's 3 things that we have to do to remember. So the first thing we're going to do is we're going to take that instruction that's trying to use the value right after the load, which was the and that it said has to move. So first we're going to insert the bubble. And the way we insert the bubble is that when we detect that they're equal, we're going to switch this mux so that this 0 goes into all of these fields. So we're just going to put this 0 through that mux. Instead of the normal control signals that cause stuff to happen in these other pipe stages, we're going to put this 0 in here. And by putting 0 in all these places, then those zeros will get staged along, and that will cause nothing to happen in any of these pipe stages, as shown in his picture. Let's look at his picture again. So see what he shows here. He shows these clouds here. These clouds mean, nothing happening. And so that's the simple objective of putting this 0 into these 3 control signals, is to make nothing happen here, nothing happen here, and nothing happen here. We've inserted a bubble, a no-op, down the pipeline. Okay, and then he said, okay, we want to move the and 1 instruction down. So the way we do that is that we take this signal, this pipe stage here, and when his clock signal comes along, we take a signal here, and we're gonna say that this register has a write enable. Write enable. We've seen that before on the register file. We're now going to put a write enable on this register here, and we're going to deassert the, what's that signal called? IFID write. Oh, IFID write, probably. Deassert the signal called IFID write. Anyway, the important point is the write part. We're going to not allow that write to occur. So when this clock edge comes along, normally what is here would go here. Instead, we're going to hold what is there. And what is there right now, sitting there right now, is that and instruction. And so by keeping this register from changing, by deasserting the write enable, by basically stopping this clock, conceptually, you can think of it as just keeping that clock from edge from happening. What we're doing is we're going to hold the and instruction and for one cycle, and he's just going to try again. So basically, he's just going to try again. And what happens, of course, is that when he tries again, he'll succeed, because the load instruction, which was here before, which is causing this hazard unit to say, oh, there's a problem, it doesn't hold, it moves to here. And so once it's moved to here, then we'll be doing the same check again. But the check again, this time it will say, oh, no problem. Okay, so the other thing that has to happen is that there's another instruction that is beating its head against this register, because we told this register to hold its value. We told it to hold the and instruction. And when we told it to hold the and instruction, well, the instruction after the and, which was about to get loaded, ends up having no place to go. And so to finish this task, we have to also deassert this signal here called program counter write. And so by deasserting program counter write, it will hold its address there, and it will read this new instruction, the one that it just got thrown away by having no place to go. It'll read it again. And then when the next clock edge happens, again, it will get latched in, it'll get registered just like normal. So the whole thing, just basically the whole front end of the pipeline just got frozen for one cycle. The back end of the pipeline moved and got made into no ops. The front end of the pipeline, the front two stages got frozen for one cycle. So we do the and decode again, and we reread the instruction after the and, whatever it was, we read it again, and then everything flows smoothly as it's supposed to in the pipeline. And again, remember that what we're going to try to do is try to never, right? We want to try to never activate. That's our goal, is to never have this happen, never have to put this bubble down the pipeline. And remember, the way we're going to do that, right, is we're going to ask the compiler to look at a little bit more code and to find something useful to do to stick between the load and the use of the load. And we saw that it can almost always do that by just finding the next load that it wants to do, because loads usually happen in groups. So it'll just go find the next one that it wanted to get, the next piece of data from your bank account data structure, and it'll bring that load forward, and then hopefully this thing, won't activate. And finally, there's one signal going to the box that we didn't talk to. We only want this box to activate if the instruction sitting here is a load. So that's this signal here called memread. So memread is the same as load. Do a load instruction. Load word equals memread. Okay. So any thoughts, questions? I explained it so perfectly and so well that everyone understands it perfectly. It seems unlikely, but we'll pretend it's true. So where is his ugly equations? Where did they go? Here it is, this one. Yeah. So here's the ugly equation. Again, just qualify it. With load word equals mem read. So we're doing a memory read, qualify it with that. And then just compare, and he just does it by taking the RT field. And again, you should read this as RD, right? We're really comparing the destination. He just grabbed the where he knows the destination field is for a load. So he's just being a little tricky there. It helps with the timing. But again, this is really RD, the RD field of the load. So conceptually, we're comparing against the destination of the load. And again, you just compare it with both RS and RT, either one, either one, causes it to have to put in a bubble, and then you stall and put in the bubble. So this is, once you understand the bypass, this is, pretty straightforward and simple. And the equations, the equation is much simpler. But again, you then have to recognize the things that you have to do. So the equation of detecting is quite a bit simpler, but what you have to do is a little bit harder. In one case, you're just switching that bypass mux. Here you got to do three things. Three things you have to remember to do. And here they are in words. You got to force the control values to 0. That's switch that mux to put a 0 through. And that will cause those 3 stages of the pipeline to become a no-op, as we showed with the X's. And then prevent the update of the program counter and the IFID register. And again, what that causes to happen is that the AND instruction, that instruction right past the load, will get decoded again. And it will cause the instruction after the AND to get fetched again. And so again, the first 2 stages of the pipeline freeze. And the load just moves on 1 cycle. And so now when you try to use its result is available for bypassing. And a key point there to note is that even after you've put in the stall, you're still going to end up, the bypass unit is still going to activate, because you're going to still want to get it right from the output of the memory. You don't want to get it, you don't want to wait till it's written into the register file. So again, we want to not have load to use. Stalls. And so again, we would like the compiler to help us do that. It says requires knowledge of the pipeline. Well, it doesn't require much knowledge. I mean, all you do is tell it, that you want to not put the use of a load right after the load, and the compiler can try and do that. But if we don't bypass and we don't get the compiler's help on this, we can throw away a lot of performance. So you'll find that a key aspect of compiler optimization is doing this. And then of course, all processors have the bypass logic in them, because that's the nature of programs. The nature of programs is that you compute a value, and then you will almost always immediately want to use that value. That's, that is just the flow of programs. That's how they work. Okay, so here is a quite a decent picture of the branch hazard. And he says that, okay, so recall that what we're going to do is we're going to do a compare two values when we do a branch, and that means that we're going to do a subtraction. And he's saying that, okay, you know, I can't get the subtraction done fast enough and get a new value available for the program counter in this time. He says, I just can't get that done in time. So he says, okay, so I'm basically gonna have to wait one cycle before I can get a new program counter. And so that means that from a branch to the target of the branch, to the instruction that is affected, you know, that is at the target, till we can execute that instruction, is 3 instructions away. So that if we do take the branch, that these 3 instructions here that we're getting just by incrementing the program counter here, here, and here, just the normal PC plus 4, that these instructions will all have to get flushed. And so that's the key point of this picture, is that if we take the load, I mean, if we take the branch like this, we go to the branch target, then we have to throw away these 3 instructions. And that is an enormous penalty. And that's typical in modern processors, that you would have to throw away a minimum of 3 instructions. Three or more instructions. And so here again, as we mentioned a long time ago, is another case where we asked Moore's law to help us out. And we did that by doing this. So we have this thing that we talked about a little bit earlier called dynamic branch prediction. And here's what dynamic branch prediction does. So we have this thing that most people call the branch history table. And the address into the branch history table is the branch instruction addresses. So that's what we're gonna look into the table with the address of the branch, because that means we've been here before. So we have the branch address, and at that address we say, oh, there's a branch, and we're going to say what did that branch do the last time we were here. So every time we come to that address where there's a branch, we look in the table, and we use what's in the table, and then if we don't do what, if we mispredict, if we mispredict the branch, we're going to update the table. So we check the table, and when it says expect the same outcome, that means we take or don't take the branch based on what the table says. What did we do last time? Did we take the branch last time? Then we're going to take the branch this time. Did we not take the branch last time? Then we're not going to take it this time. So we're using history, to predict the future. And the more transistors we have available for us using Moore's law, the more history that we can use. And when I say the more history we can use, that means that there's many paths that you can take to get to a particular branch. So the flow of a program is dynamic, right? You're going all over the place based on if then else statements. And so you can get to the same branch location from many different paths. And the more of those different paths that you're able to distinguish, the better your branch predictor can be. And the only way to distinguish those different branches is to store the history of the pattern of how you got here. So the pattern that you got here this time might be branch, 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 branch. Or it could be branch, not branch, branch, not branch, branch, not branch. Or it could be branch, not branch, not branch, not branch, branch. I mean, there's infinite number of different patterns of branch that you could get to this one. And if you look at the pattern you came to it with, and you use that, you use the history that you stored for that pattern, then your prediction can be very good. If you have a branch history table that only has one history bit in it, I mean one bit that says which way to go, then your prediction can be good but not great. So it all depends on how many transistors you throw at this problem as to how good your branch predictor will be. And so the rest of the steps, right, is okay, you start fetching from either the fall through or the target, again, depending on whether it says take the branch or don't take the branch in our history table. What did we do last? What did we do last time? So what happened to my pen? What did we do last? And then again, you change, you update. If you're wrong, if you ultimately, when you finally compute, when you finally get to where you know whether you were supposed to have branched or not, and that's a key point here, is that all this branch prediction is being done up front before you actually do the branch comparison and figure out whether you want to really take the branch or not. We're doing all this with a whole bunch of hardware up front that guesses immediately rather than waiting for the branch comparison and the all the other stuff that has to happen, switching all the muxes and everything. We're not going to wait for any of that. Instead, we're going to do it immediately up front. So here's, just to give you an idea of the subtleties involved here in terms of how many different paths you want to take. Here's the first order subtlety that was immediately noticed when they built the very first branch predictor that they immediately solved. They said, oh, look at this case here. If we only have a 1-bit predictor, they said, here's what'll happen. If you go into an inner loop and you're sitting there going around the inner loop, that when you get to the branch at the end of the inner loop, you'll have been going taken, because you're going back each time, taken. And then when you fall out, all of a sudden it'll be because you fell out of the loop and now you'll have not taken the branch. And so by our rule, that would cause us to flip the bit so that, because we want to know when we get to the branch, we always know what we're going to use history to tell us what to do. So we want to know what we just did. So we'll switch it to say untaken. And then many loops, as we know, for example, the multiply loop, are nested loops. And so you go around the outside of this loop and then you come back in. And you can see the problem that when you now get to the very bottom of this loop that you're going to take 20 times, say, you're doing maybe a 20 by 20 multiply instead of 4 by 4. you're gonna do that thing 20 times, but the first time, since you flipped it to not taken when you fell out, now you're gonna have it not taken, and so you're not gonna take it, but you really did want to take it because you want to go around the loop. And so you mispredict twice for no good reason whatsoever. So we mispredict on the last iteration of the inner loop, and then we mispredict on the first iteration of the inner loop when we come into the next time. So that's what happens to us. And so we immediately fix that problem with this beautiful little diagram here. And guess what this is? This is one of our favorite things. This is an FSM. So this is another FSM that we have on our processor, another finite state machine that we have on our processor to help us learn. So this is about the simplest, the simplest AI machine that you could imagine. So instead of 2 bits, here was our 2 states before that we had. Instead, we add these 2 more states over here that are, that are like saturating states. So after you take it one time, if you then take it again, you'll go over here. And then after you do that, you'll just stay in this loop here if you keep taking. And then notice that now if we fell out of the loop, we would go to here. And so if we only fall out one time, we'll still say predict taken. So the next time we came in, we've got this one level of hysteresis that will cause us to not mispredict the next time we go into that inner loop. But if we miss twice, if it's not that kind of a construct and we miss again, we'll then go to here. And now we'll be in the not taken thing, and you can saturate over here in the not taken as well. So this is completely symmetric, and it solves that that immediately obvious problem, the loop problem. But it turns out that this mechanism is not just good for that loop problem. It's good for a lot of different types of program constructs, where another fancy word here, a tiny bit of one state of hysteresis. I don't know if that's how you that's not right. Hysteresis. One cycle of hysteresis, or one state of hysteresis is very, very helpful. But this is just the very simplest first thing that was done in branch predictors. Now they're 100 times more sophisticated than this. And again, what they do is they follow multiple paths in. So that was just one path in, but we could have one of these history tables for any number of different paths coming to the current branch. And that's how modern processors are. They'll have many different paths coming into the same branch, and they'll use the predictor. They'll still have a 2-bit predictor, because this turns out to be the very best thing to have at the very end. But that 2-bit predictor will be gotten to from many different paths. And again, it's just a matter of how many transistors, how much storage you're willing to throw at the problem. Okay, so you still, had to figure out where to go, and we don't want to do that either. So we don't even wait to compute the branch target. Once we see that an address has a branch, we build this thing called a branch target buffer. And that's a memory. Again, cache and memory cache is just a kind of memory. But cache means, remember, it means a subset of the whole. So we don't have all of the branch addresses stored. We just have some of them, and that's why it's called a cache. So we have the most recent addresses of branches. And so basically what we're doing is we're looking into that thing and we're saying, okay, if this address is a branch, then spit out to me where I was supposed to go. And so that's what we do. We put the PC in there, right, into this thing. And if the instruction is a branch, we immediately know where to go. We can fetch the target immediately. And so again, this is all part of prediction. So we're gonna predict that if it's a branch that it will be taken, and so we want to know where to go. Because the other case is easy. If we don't take it, we just go to the next instruction. So we've always got the two places that we can possibly go. That's what we need. With any branch, there's only two things that can happen. Either go to the next instruction or you go to the target. And so we always want both of those available. And so that's what we do by putting in this branch target buffer. Lots of transistors, but gets rid of throwing those three instructions away, you know, every time we're wrong about which way to go. Okay, so we'll just say a few words here about exceptions and interrupts, and then we'll do tonight's quiz. The beauty of exceptions and interrupts is that it turns out that they look really like procedure calls. So remember with a procedure call, when we called a subroutine or a procedure or a function or a method or whatever you want to call it, remember we had to store the address of where to come back to. And then we went to the target of the procedure call. So we went to the target, and then we had to store away where to come back. And for exceptions and interrupts, basically we have to just do the same thing. Where we go isn't specified by the program. When you have a procedure call, you say call square root, and you tell it, right, you know, that square root is, the address of the square root is embedded right there in that call. Here for exceptions and interrupts, it turns out, you know, we always go the same place. We go to the operating system. So we don't need the program to tell us where to go. We just know that if we have, and let's forget about exceptions for a moment. If we have an interrupt, and an interrupt just means that the processor is sitting there doing something, and all of a sudden, you know, you press one of the keys on your keyboard, and the processor says, "Oh, I need to go and figure out what he wants me to do," and I'll get that character and, you know, and put it into the whatever he's doing, sending a text or whatever. So that's what interrupts are for. It's the, you know, the processor is sitting there doing something that isn't interrupt driven, and then it gets an interrupt again, like you pressing a key. And so, but the way the processor handles an interrupt is it goes off to the operating system, and it knows where the operating system is, so you don't need the address. You've got it stored right there on the processor. There's only one place that it goes to. So that's what takes the place of the name of the procedure that you're calling. And then where to come back to works just like a procedure, except we have a separate register. We don't, it's not part of the general purpose registers, because when we come back from an interrupt, we want to be able to continue running just as if nothing had happened. So we don't want to, we can't write over the standard register that we use for returning from a procedure. So instead we have an exception register, the so-called EPC register, which we'll see in a second here. So anyway, the important case here is this one, an interrupt, again, from an external IO controller of some sort. And an external IO, again, you know, for the simplest case is, you know, just a key press. That's external IO when you press a key. And when you press a key, you want, you know, something to happen, you know, fast. And so, you know, so when we when we come back on Thursday, we'll look at the details of handling these interrupts a little bit, and then do the rest of the more interesting stuff. We won't spend much time on it because there's a bunch of ugly schematics and whatever. But we want to do the tonight's quiz. Let me find it.
No. You need to use all of those. What is the exact text of the question? What are the options? It's either that or the perpendicular force, and I'm not sure which. Probably trig functions.
Hello?
Yes.
Excuse me? Um,
Yes.
I muted. I think I muted. Hang on.
I can hear you. He's not.